Hello there, and welcome to the Sleep Porch. Tonight, we'll be exploring the mesmerizing world of shooting stars. Those brief flashes of light that have captivated humanity for thousands of years, that appear for just a heartbeat, but disappear before we can be sure we even saw them. People marvel at their rare beauty, savoring the time to make a wish. But behind that simple moment is a powerful cascade of forces from the depths of outer space. Every shooting star is part of a much larger story, shaped by drifting dust, wandering objects, and the steady movement of Earth itself. These lights are not rare accidents or distant spectacles. They are ongoing events woven into the nightly rhythm of the sky, happening whether anyone is watching or not. Some are subtle and delicate, others brilliant and commanding, but all of them hint at a universe that is active, layered, and endlessly surprising. In this video, we'll explore how shooting stars move, where they actually originate, and why they've captivated human attention ever since we first gazed into the night sky. If you enjoy these gentle explorations, I invite you to like, subscribe, or leave a quiet thought below. It helps others discover this space as well, one sleepy soul at a time. But for now, there's nothing you need to do except rest. Let your eyelids grow heavy and your body gently unwind. Allow your thoughts to slow as we drift into these cosmic wonders. Let's begin. Shooting stars are not stars at all, but tiny pieces of rock from outer space. What appears as a star falling through the sky is actually a small object entering Earth's atmosphere at extraordinary speed. These objects have been orbiting the Sun unnoticed and unlit until their paths intersect with our planet. They do not glow in space, and they do not resemble fire until the moment they hit our atmosphere. As they plunge into it, they collide with gas so forcefully that intense heat is produced almost instantly. That heat causes the object to erode and the surrounding air to glow, creating the familiar streak of light. The glow is so short because the interaction itself is brief. Most of the material is destroyed high above the ground, never reaching the surface. By the time your eyes register what happened, the event is already ending. Many shooting stars are smaller than a grain of sand. The size of the object has very little to do with how dramatic the display appears. A particle so small you could barely see it in your hand can still produce a bright streak across the sky. That is because speed, not mass, supplies most of the energy. When a tiny object enters the atmosphere at extreme velocity, it transfers energy into the surrounding air, lighting up a long path rather than a single point. The atmosphere spreads that energy out, turning something microscopic into something expansive and visible. This is why the sky can look calm while being constantly bombarded by space debris. Most of it never produces light bright enough to notice. Only a small fraction creates visible meteors. The ones you see are the rare moments when size, speed, and angle align just right. In reality, Earth is interacting with countless tiny visitors every day, almost all of them passing without spectacle or awareness. They can enter Earth's air faster than 60 kilometers per second. At these speeds, the atmosphere does not behave gently. Air cannot move aside quickly enough, so it is compressed violently in front of the incoming object. That compression produces intense heat and light in a fraction of a second. The meteor does not slowly warm up or gradually slow down. Instead, enormous energy is released almost instantly, which is why meteors often appear suddenly and vanish just as fast. The speed also determines how the meteor looks. Faster entries, tend to produce sharper, more sudden streaks, while slower ones can appear longer and smoother. This speed comes from the combined motion of the object and Earth itself, as both travel around the Sun. When they meet head-on, the result is extreme velocity. What you are seeing is not just an object falling, but orbital motion made visible. For a brief moment, the scale and speed of the solar system reveal themselves in the night sky. Most shooting stars never reach the ground, and they vanish completely. After the flash, it can feel like something must keep falling, but almost nothing does. The incoming object is being shaved away so quickly that it turns into hot vapor and ultrafine dust long before it ever gets near the surface. The bright streak is the short window when the atmosphere is doing the work of dismantling it. As the object breaks down, it leaves behind a thin trail of particles that can drift on high winds for days, spreading far from where you saw the light. In a sense, the sky does not swallow the object in one bite. It dissolves it into ingredients. This is why the world is quietly accumulating space material without anyone noticing. Even if you watched the meteor from start to finish, there would be nothing to find afterward. Not because you missed it, but because the atmosphere finished the job completely. The show ends high above you, and the rest becomes invisible. If a fragment survives to land, it becomes a meteorite. Sometimes the object is tough enough that the atmosphere cannot erase it entirely. After the bright part of the flight ends, the remaining piece slows down so much that it stops glowing, and it drops the rest of the way in darkness. That hidden descent is called dark flight, and it is why a meteorite can land far from where the fireball looked brightest. On the ground, it may arrive with no drama at all, a stone thudding into soil or snow, while the sky above appears calm again. Fresh meteorites often have a thin, blackened skin, formed by brief surface melting, which can make them look like they have been toasted. They are rarely hot all the way through, because the heated outer layer is stripped away during flight. When one is recovered quickly, it is a direct physical link to space that bypassed every rocket and every mission plan. It is a delivery, not a discovery, and is arrived on its own schedule. Meteorites can be older than Earth, preserved from solar system formation. Earth is constantly reworking itself. Rocks melt, mountains rise and erode, oceans recycle the seafloor, and time scrubs away early history. Many meteorites avoided all of that. They formed when the solar system was still assembling, when dust and small bodies were colliding and clumping together around the young sun. Some never became part of a large planet, so they never experienced the deep melting and reshaping that would erase their earliest features. They spent ages in space, cold and dry, keeping early minerals and textures intact. When one arrives on Earth, it can carry materials that have barely changed since the solar system's first chapters. In laboratories, scientists can read that record using the chemistry of minerals and the ratios of isotopes locked inside them. The result is a strange reversal. A rock that falls from the sky can tell you more about the beginning of our neighborhood than most rocks under your feet. The bright fireball can outshine every star in the sky. Fireballs occur when the incoming object is larger or more cohesive than average, allowing it to release far more energy before breaking apart. In these cases, the light can rival or exceed that of any planet or star, briefly becoming the brightest thing in the sky. The sudden brightness can be startling, sometimes illuminating the ground or nearby objects. This does not mean the object is about to strike the surface. Most fireballs still disintegrate high above Earth. Their brightness comes from how much energy is released in a short span of time, often as the object fragments into multiple pieces. Because they are rare, fireballs tend to leave strong impressions. Many people remember them clearly, even years later. For a few seconds, the usual order of the night sky is disrupted, then restored just as quickly. The stars return, the darkness settles, and the moment passes without leaving anything behind. Meteor showers happen when Earth plows through old comet dust streams. Comets shed material as they travel near the Sun, leaving behind long trails of debris along their orbits. These trails persist for thousands of years, forming regions of space filled with tiny particles. When Earth passes through one of these regions, many particles enter the atmosphere over a short period, producing a meteor shower. The increase in activity is not caused by anything new arriving, but by Earth moving into an already crowded path. This is why meteor showers occur at roughly the same time each year. The particles approach from similar directions, making the meteors appear to radiate from a single point in the sky. That point is a matter of perspective, shaped by Earth's motion. Meteor showers turn random-looking events into predictable patterns, allowing observers to know when the sky is more likely to come alive with movement and light. Most meteors begin glowing about 100 kilometers above your head. This is far above clouds, storms, and aircraft, in a region where the atmosphere is thin but still present. A meteoroid can travel through space invisibly for millions of years, then suddenly announce itself the moment it reaches this altitude. The glow begins when air molecules are compressed and heated in front of the object as it rushes downward. Because this happens so high up, meteors can be seen over enormous distances, sometimes by people hundreds of kilometers apart. Each observer sees the same event from a different angle, making it feel local even though it is not. This height also explains why meteors seem to belong more to space than to the sky we experience every day. They are not interacting with weather or clouds, but with a thin edge of atmosphere that acts as Earth's first line of contact with the solar system. What feels close is actually happening far beyond anything we ever physically reach. A meteor's color hints at chemistry, like sodium yellow or copper green. Not all meteors look white. Some flash yellow, others tint green, and a few show brief or bluish tones. Those colors can come from elements vaporizing and emitting light at specific wavelengths as they interact with the surrounding air. Sodium can push a meteor toward a warm yellow. Copper can contribute a green tint. Calcium can lean toward a purplish tone in the right conditions. The atmosphere itself also plays a role, adding its own glow to the mix, especially when nitrogen and oxygen are excited by the shock of entry. This means your eyes are not only seeing motion, they are seeing composition hinted at through color. It is not a perfect chemical test from the ground, but it is a real clue that many observers notice even without equipment. A meteor that looks oddly green is not doing it for style. It is revealing something about what is being heated, what is being vaporized, and what kind of atoms are briefly lighting up the sky. The same meteor can change color as different layers vaporize. A meteorite is rarely a perfectly uniform lump. It can contain different minerals, tiny metal grains, and weaker zones that crack under stress. As it heats, the outer surface may release one set of atoms that glow in a certain color. Then, the object can split, exposing fresh interior material that burns differently, and the color shifts. Sometimes the change happens as a gentle transition. Other times it arrives as a sudden flare when fragmentation creates multiple bright points at once. This is why a single meteor can appear to throb or shimmer, not because the sky itself is flashing, but because the object is altering its shape as it breaks apart. Shifts in color also suggest temperature variations along its path, since different materials vaporize at different rates. Within just a few seconds, the meteor can expose layers that remained hidden for ages, splitting itself open as it descends. What follows is a fleeting series of signals, arriving too quickly to fully describe, yet distinct enough to linger in memory. Most of the brightness comes from energized air molecules rather than the rock itself. The luminous trail is not simply the object glowing like a spark. Much of the light you see is created by the atmosphere. As the meteoroid tears through, it energizes and ionizes the air along its path, knocking electrons loose and leaving behind a trail of charged particles. When those particles recombine and settle back toward normal, they release light. The result is that a tiny object can create a luminous path far larger than itself because the air around it is doing a lot of the shining. This also explains why the trail can look thicker than you would expect, and why the brightness can persist briefly even as the object is breaking apart. The meteor is the trigger, but the atmosphere is the material being lit up. In a very real sense, the night sky is briefly showing you a changed state of air, one that is normally invisible. For a moment, you're watching Earth's atmosphere respond to a visitor from space by turning itself into light. A meteor can be silent to you, yet roar loudly high above. When a bright meteor flashes across the sky, your eyes receive the light almost instantly. But sound follows different rules. The event is happening high above the ground, often many tens of kilometers up, where air is thin and distances are large. Any sound created by the meteor's passage must travel all the way down through layers of atmosphere before it can be heard. That journey takes time. As a result, the sky can appear explosive while everything around you remains completely quiet. When sound does arrive, it may come seconds or even minutes later as a distant boom, rumble, or series of cracks. The delay can feel disorienting because it breaks the expectation that sight and sound belong together. In some cases, the sound never reaches the ground at all, fading away before it arrives. This creates the strange experience of witnessing something powerful without hearing it, as if the sky acted alone. The silence is not evidence of weakness. It is simply distance made noticeable. Some people report simultaneous crackles, likely from unusual radio effects. A small number of observers describe hearing faint crackling or sizzling at the exact moment a bright meteor appears, even though normal sound should arrive later. This has puzzled scientists for decades because it seems to ignore the rules of sound travel. One explanation involves electromagnetic waves produced when a meteor ionizes the atmosphere along its path. These waves move at the speed of light and can reach the ground instantly. If nearby objects are capable of responding to those waves, they may vibrate slightly and produce sound right where the observer is standing. Thin materials such as dry leaves, grass, hair, eyeglass frames, or lightweight metal objects are often suggested as possible converters. The sound would not be coming from the meteor itself, but from the environment reacting locally. The effect is difficult to confirm because it is rare and unpredictable. Still, reports have come from different locations and time periods. If correct, it means some meteors briefly change not just the sky, but the invisible energy around you. Some meteor showers last for weeks because their streams are spread out. a meteor stream is not always a narrow ribbon. Over time, dust released at slightly different speeds spreads out along the parent orbit, turning a tight trail into a long, diluted band. Planetary gravity can also tug different parts of the stream in different ways, widening the region Earth passes through. The result is a shower that does not arrive like a single appointment, but like a season, with a slow build, a peak, and a gradual fade. This is why you can catch members of some showers on many nights, even when the peak is past. It also explains why two showers can feel completely different. One can explode in a brief, intense window, while another keeps returning in small doses night after night. Long-duration showers reward patience because the sky stays in a heightened state of possibility for a long stretch. Even a casual look upward can catch a stray member, like finding a clue outside the main event. A meteor can appear to curve, though its path is nearly straight. Meteors travel on paths that are essentially straight during the visible portion of flight. Yet your eyes can report something different. A long meteor near the edge of your vision can seem to bend as you try to follow it, because your gaze shifts while the streak is still forming. The sky is also a curved surface to your perception, and straight lines across a dome can look subtly warped depending on where they appear. Near the horizon, the effect can be stronger because you have fewer reference stars and more visual distortion from looking through thicker air. Fragmentation can add to the illusion, making a straight path look kinked when a bright piece breaks off and flares slightly apart. The result is a moment where you doubt what you saw, even though the physics is simple. This is part of what makes meteor watching so addictive. The event is real, but your perception is working at its limits, trying to interpret something fast and unfamiliar. Some meteors leave glowing trails that linger for minutes. After the bright streak fades, a faint line can sometimes remain suspended high in the atmosphere. This trail is not falling debris, but disturbed air that continues to glow after being energized by the meteor's passage. At those altitudes, winds move differently than near the ground, and the trail can slowly bend, twist, or stretch as it drifts. Watching this transformation reveals motion in parts of the atmosphere that are normally invisible. The meteor itself is gone almost immediately, but its interaction with the air continues to evolve. These lingering trails can last for several minutes before fading completely. They turn a brief event into a slow one, replacing sudden motion with gradual change. The sky seems calm again, yet something is still happening far above. Once the trail finally dissolves, there is no sign it was ever there, as if the atmosphere has quietly closed behind the event. A single meteor can shed metal atoms that help form knowant clouds. As meteors erode in the upper atmosphere, they release atoms such as iron and magnesium. These atoms can combine into extremely fine particles that remain suspended at very high altitudes. Under specific conditions, those particles become the seeds around which ice crystals form, creating noctilucent clouds. These clouds appear long after sunset or before sunrise, glowing because they are high enough to reflect sunlight while the ground is dark. They are among the highest clouds in Earth's atmosphere and cannot form without these microscopic inputs from space. This creates a quiet connection between a fleeting meteor and a structure that may appear days later. The meteor itself is gone, but part of it remains, influencing atmospheric processes far above weather and storms. A brief streak of light can contribute to a cloud that lingers in the sky, linking momentary events to slow, delicate atmospheric formations. The Perseids return each year from debris of comet Swift-Tuttle. This well-known meteor shower occurs when Earth intersects a dense stream of particles left behind by a large comet. Swift-Tuttle follows a long orbit, and each time it passes near the Sun, it releases material that remains spread along its path. Earth crosses this path every summer, producing the Persians. The meteors are fast and often bright, making them easy to spot, even for casual observers. Records of this shower stretch back centuries, long before its source was identified. That consistency reflects the stability of the debris stream, rather than ongoing activity from the comet itself. The comet may be far away, but its past journeys continue to shape what we see in the sky. Each meteor represents a separate fragment of that history, intersecting Earth's atmosphere on a schedule set by orbital motion, rather than chance or coincidence. The Geminids come from an asteroid-like object called Thal. Unlike many major meteor showers, the Geminids originate from a rocky body rather than a classic icy comet. Phaethon follows an extreme orbit that brings it very close to the Sun, where intense heat stresses and fractures its surface. That process releases debris, creating a dense stream Earth encounters every December. The resulting meteors are often bright and steady, with paths that are easy to follow across the sky. Because the particles are relatively dense, they tend to survive longer during entry, producing well-defined streaks. The Geminids challenge the idea that only comets can create meteor showers. They show that sunlight alone, acting on rock, can supply material to near-Earth space. Each December, Earth passes through debris shaped by heat rather than ice, revealing another way the solar system continuously feeds motion and light into our atmosphere. Some meteorites contain tiny grains that formed around other stars. Inside certain meteorites are microscopic crystals that did not form in our solar system at all. Long before the Sun existed, other stars were shedding material into space, and some of that dust cooled into solid grains. Those grains drifted between stars, mixed into the cloud that later formed our solar system, and became trapped inside growing asteroids. They are rare and incredibly small, so finding them is a careful process. Researchers dissolve away much of the surrounding meteorite with strong chemicals, then isolate the stubborn grains that remain. The proof is in their isotopes, which carry patterns that match processes known to occur inside stars. It is one of the most direct ways science has confirmed that material from other stellar systems ended up here. A meteorite can therefore contain multiple histories layered together. Part of it formed near our Sun, while some specks inside it began their lives around completely different stars in a different time. Those pre-Ola grains predate our Sun, making them cosmic fossils. A fossil usually suggests bones or shells, but these are fossils of environments. Each grain preserves conditions from a star that lived and died before our solar system formed. Some were forged in the slow winds of aging red giants. Others carry signatures linked to violent stellar explosions. They survived an impossible sequence of events, being created near a star, escaping into interstellar space, enduring radiation and collisions, and then avoiding destruction during the chaotic birth of planets. That survival is what makes them precious. They are not common ingredients sprinkled evenly through meteorites. They are rare survivors that had to avoid being melted or chemically reset. When scientists examine them, they're not only identifying what they are made of, but reconstructing what kind of star produced them and what kind of conditions surrounded their formation. These grains turn meteorites into archives of worlds that never became planets and stars that disappeared before Earth existed. They are ancient in a way that Earth's rocks almost never are. Iron meteorites can preserve patterns known as Widmanstätten structures, formed over vast stretches of time. When an iron meteorite is sliced and polished, it may reveal an inner geometry that feels nearly engineered, intersecting bands that repeat with quiet precision. This pattern can only develop if the metal cools at an extraordinarily slow pace, usually within a large parent body, where heat leaked away over immense periods. On Earth, metal rarely cools with such patience, which is why this structure is regarded as strong evidence of an origin in space. The bands arise from different iron-nickel minerals separating as temperatures fall, forming a natural arrangement that records the meteorite's cooling history. In essence, the interior becomes a visible timeline. This is why collectors and scientists value slices of iron meteorites. They do not just display metal, they display the hidden interior conditions of a long-gone body that once held molten iron like a tiny core. You are looking at a structure that took ages to grow, revealed in one moment by a cut. Air resistance heats meteors, not friction in the everyday sense. It is easy to imagine a meteor heating up like hands warming by rubbing together. But that picture misses the real source. At meteor speeds, air cannot flow smoothly out of the way. It gets squeezed hard in front of the object, forming a compressed region where temperature rises sharply. This hot, compressed air transfers energy to the meteoroid surface, which then melts and sheds material. The heating is driven by violent compression and shock effects, not gentle rubbing. This is why even a small object can light up so intensely. The atmosphere becomes a powerful engine that converts speed into heat almost instantly. The process is also why the brightest part of the meteor can happen suddenly when conditions shift and the compression intensifies. You are seeing a high-speed collision with air, with the atmosphere acting like a dense barrier for a fraction of a second. Understanding that makes the event feel less like burning and more like a brief, extreme interaction between motion and gas. Meteor trails can reflect radio waves, enabling brief, long-distance signals. As a meteor tears through the upper atmosphere, it can leave behind a narrow trail of ionized gas filled with charged particles. For a short time, that trail can act like a reflective surface for certain radio frequencies. Radio operators have learned to use this effect by aiming signals at the sky and waiting for a meteor trail to appear. When it does, the signal can bounce off the trail and travel far beyond its normal range. The opportunity is brief. Trails may last only fractions of a second before breaking apart, which forces messages to be sent quickly in short bursts. During active meteor showers, the number of available trails increases, making communication more frequent. This technique works even when the meteor itself is not visible to the eye. It is a quiet reminder that meteors do more than create light. They temporarily reshape the atmosphere's ability to carry information. A streak that lasts a heartbeat can briefly turn the sky into a relay station, linking distant points through a path that vanishes almost as soon as it forms. Radar can detect meteors you never see, even in daylight. Human vision captures only a small portion of meteor activity. Radar systems can detect much more by sensing the ionized trails meteors leave behind. When radar waves encounter these disturbed regions of the atmosphere, some of the signal is reflected back, revealing the presence of a meteor, even if it was too faint, too small, or hidden by daylight. This allows scientists to study meteors around the clock, regardless of weather or lighting conditions. Radar observations show that Earth is constantly receiving material from space, not just during well-known showers. They also reveal patterns in speed, direction, and timing that are impossible to see with the eye alone. Daytime showers, background meteorites, and subtle changes throughout the year become visible through data instead of darkness. In this way, radar turns the atmosphere into a giant detector, reading the signatures left behind by incoming particles. Even when the sky looks empty and blue, the instrument can show that countless meteors are still arriving and dissolving above you. The daytime Arietids are one of the strongest showers, hidden by sunlight. The erratids occur when Earth crosses a dense stream of debris during daylight hours, making them invisible to most observers. The radiant lies close to the sun's position in the sky, which means any visible streaks are overwhelmed by brightness. Despite this, radar and radio observations reveal that the shower is remarkably strong, producing a high rate of meteors each year. The activity peaks when people are going about ordinary routines, completely unaware that the upper atmosphere is busy with incoming particles. This makes the Arietids a striking example of how meteor showers are not performances arranged for nighttime viewing. They are simply intersections of orbits that happen whenever geometry dictates. The shower reminds us that the sky does not become active only when we are watching. It is active according to schedules set by planetary motion. Without instruments, this entire event would pass unnoticed. With them, it becomes clear that one of the year's strongest showers is taking place in plain daylight, hidden by the sun. Meteorites can spike in bursts when Earth hits denser dust filaments. Meteor streams are not evenly spread clouds of debris. They often contain narrow filaments where particles are packed more tightly. These filaments formed when material was released during specific moments in a comet's past, then shaped by gravity over time. When Earth passes through one of these denser strands, meteor rates can rise suddenly and dramatically for a short period. An otherwise quiet char without warning, then settle back down as Earth moves on. These bursts reveal structure inside something that otherwise seems invisible and smooth. They also make prediction difficult, since slight changes in Earth's path can mean missing or striking a filament. Observers may notice sudden clusters of meteors that feel unexpected, even during well-studied showers. Each burst is a brief crossing of a concentrated ribbon of debris laid down long ago and preserved by orbital motion. The sky is not changing its mood. Earth is simply moving through regions of different density, and the atmosphere reveals that structure through light. The Leonids sometimes produce storms thousands per hour in rare years. Most meteor showers are modest, offering scattered streaks over the course of a night. The Leonids are different. In certain years, Earth passes through especially dense parts of the stream, producing what are called meteor storms. During these events, meteors can appear so frequently that the sky seems continuously active, with streaks arriving every few seconds. Historical accounts describe skies filled with motion, where looking anywhere reveals another meteor. These storms are rare and short-lived, often lasting only an hour or two, which makes them legendary among observers. The difference between an ordinary Leonid year and a storm year is dramatic, even though the calendar date is the same. What changes is Earth's exact position relative to dense filaments in the debris stream. This makes the Leonids a reminder that meteor showers have deep structure and long memory. When conditions align, the result is not just a shower, but a sky crowded with motion, shaped by material released centuries earlier. The Leonids trace back to comet Tempel-Tuttle's repeated returns. This MEO exists because a comet has been revisiting the inner solar system for thousands of years. Each time the comet passes near the Sun, it sheds material that spreads along its orbit. Over time, these releases form multiple strands with different densities and ages. Earth crosses this complex structure every November, encountering debris from various pastages. Some of the most intense Leonard storms are linked to material released during specific returns, which means the meteors can be traced to particular moments in the comet's history. The comet itself may be far away during the display, but its orbital path remains marked by the debris it left behind. This creates a long-term relationship between Earth and the comet, one based on repeated crossings rather than direct encounters. The Leonids show how comets reshape space through persistence. Their influence does not end when they disappear from view. It continues each time Earth revisits the trails they carved through the solar system. The Draculids can be slow, giving unusually gentle drifting meteors. Compared to many meteor showers, the Draconids often arrive at slower speeds. This difference changes how they appear in the sky. Instead of sharp, sudden streaks, some Draconids seem to glide, giving the impression of softer motion. The slower entry allows the light to linger slightly longer, making individual meteors easier to follow with the eye. This can give the shower a calmer character even when activity increases. The Draconids are also known for unpredictability. Some years bring little activity, while others produce sudden surges that surprise observers. Because the radiant is often high in the evening sky for northern viewers, a shower can be watched earlier than many others. This combination of timing, motion, and variability gives the Draconids a distinct identity. They feel less like flashes and more like moving points, changing how the atmosphere lights up. When one appears, it invites tracking rather than surprise, revealing another way meteors can behave. The Draconids are linked to comet Giacobini-Zin's dust. This meteor shower originates from material released by a comet whose orbit crosses Earth's path. As the comet travels, it sheds dust that forms an uneven stream in space. Earth encounters this stream in early October, producing the Draconids. Because the debris is clumpy rather than smooth, activity levels can change sharply from year to year. Some passages bring only a few meteors, while others produce sudden outbursts that last a short time. These variations are tied to how the dust was released and how gravity has shaped it since. The radiant lies in the region of Draco, which can place it well above the horizon during evening hours, making observation easier. Each meteor represents a fragment of the comet's past, arriving when Earth's orbit intersects the right part of the stream. The Shah is a reminder that comet debris does not disperse evenly. It remains structured, carrying a record of its release, and Earth reveals that structure by passing through it. The Taurids often produce bright fireballs from a broad debris stream. Unlike many showers that feel concentrated into a tight peak, this one is spread out, and that matters. The Taurids arrive in a wide, messy stream linked to Comet Encke, so the background activity can simmer for weeks. What makes people remember them is not the sheer number of streaks, but the chance of a slow, heavy-looking fireball that brightens in step. Some Taurids fragment late and flare like a camera flash, as if the sky briefly switched on a spotlight. The shower is slow compared with many others, which can make the brighter ones easier to track with your eyes. There are even seasons when observers mention a Taurid surge, when fireballs appear more often than expected. That possibility adds tension to the experience, because even a calm stretch of time can suddenly be broken by a clear, brilliant flash of light. Meteor showers also have what are known as radiant points, where their paths seem to spread outward. During a shower, meteors show up across many regions of the sky, yet they appear to share a common, unseen source. If you extend their trails backward, they converge toward a single area known as the radiant. This does not mean the meteors originate from that spot. It is a geometric illusion created by countless particles moving along nearly parallel paths as they encounter Earth. The radiant is useful because it turns a sky full of brief flashes into something you can identify and name. It helps observers tell whether a meteor belongs to the shower or is just a random sporadic streak. Radiance can also shift slightly from night to night as Earth moves, which means the shower has a changing center rather than a fixed target. Once you learn to look for it, the sky stops feeling random and starts feeling structured, like you are watching an organized flow. The radiant effect is perspective, like parallel train tracks meeting in distance. The meteors in a shower are moving through space in roughly the same direction, but your eyes see their paths projected onto a dome of sky. Parallel motion can look like it comes from a single point when viewed in perspective, just as straight tracks appear to converge far away. That is why shower meteors can streak across completely different constellations, yet still seem connected. The radiant is the direction Earth is facing into the stream. So the meteors appear to come from ahead, not from behind. This also explains why shower meteors seen near the radiant often look shorter. They are coming toward you more directly, so less of their path is visible sideways. Farther from the radiant, the same kind of meteor can draw a long line because you are seeing it from the side. Once you understand this, the shower becomes three-dimensional. You are not watching isolated streaks. You are watching the flow and your viewpoint inside it. Your brain and horizon distortions can make meteor paths look bent. A meteor gives your brain almost no time to measure distance, speed, or direction. In that rush, perception fills gaps using context, and the horizon is full of tricks. The lower sky is where you misjudge angles most, because buildings, trees, and the slope of the landscape add cues that do not match the actual geometry overhead. The same street can seem steeper, flatter, or even slightly curved, depending on where you were looking a moment before it appeared. There is also the problem of memory. You reconstruct a path after it is gone. And reconstruction can quietly add shape that was never there. This is why two people can watch the same meteor and describe it differently, without anyone lying. The event is brief and the brain is fast, but it is not a perfect measuring instrument. Understanding these distortions does not ruin the experience. It makes the experience sharper because you start paying attention to how the sky and the mind cooperate to create what you think you saw. The same meteor can be seen from turns hundreds of kilometers apart. Because meteors glow high in the atmosphere, a single bright event can be visible across a wide region. One person may see it low in the north, another may see it high overhead, and a third may think it moved in a completely different direction. These differences come from viewing angle, not from multiple meteors. The same path in space is being projected differently onto each observer's sky. That wide visibility is why bright fireballs generate floods of reports within minutes. People who never talk about astronomy suddenly compare notes, trying to make sense of what they witnessed. It can feel like a shared interruption, a brief event that synchronizes strangers who are far apart. This is also why witness accounts can sound contradictory at first. A meteor that seemed to skim the horizon from one town can look like a steep plunge from another. When those viewpoints are combined, the true path often becomes clearer. A single streak can connect a whole map of people through one moment of light. Two observers can triangulate a meteor's height using timing and direction. If two people record the same meteor from different locations, their separate viewpoints become a measuring tool. Each observer notes where the streak appeared against the star background, when it started, and when it ended. Those directions define two lines of sight that intersect in three-dimensional space, allowing the meteor's altitude and track to be estimated. With good timing, the speed can also be inferred, turning a fleeting flash into a reconstructed trajectory. This is not a vague guess. It is geometry working with the sky as a reference grid. Even simple smartphone timestamps and careful descriptions can contribute, especially when paired with fixed camera footage. Triangulation is one of the reasons meteor science can feel so approachable. You do not need a rocket to study objects from space. You need two viewpoints and careful notes. The meteor is gone, but its path can still be mapped like tracing a thrown stone after it disappears into darkness. Many countries run fireball networks to predict meteorite fall zones across the world. Wide-angle cameras watch the night sky automatically, night after night, waiting for bright fireballs. When one appears, multiple stations can capture it at once, producing a precise record of its path. Software then compares the footage, measures the angles, and reconstructs the trajectory through the atmosphere. From that, scientists can estimate where surviving fragments might have landed, narrowing the surge to a manageable zone instead of a whole countryside. These networks turn chance events into recoverable opportunities. They also create archives, revealing how often fireballs occur and how they behave across seasons. Some networks operate in deserts, some across farmland, some across remote landscapes where the sky is dark and cameras can see more. The remarkable part is the purpose. The goal is not only to watch something beautiful, it is to catch a physical sample of space before rain, soil, and human handling blur the evidence. A fireball network is a quiet promise that if the sky delivers a rock, someone is ready to follow the trail. Some meteorites are recovered within days before weather alters them. A freshly fallen meteorite carries delicate clues on its surface and inside its cracks. Time on Earth starts changing it immediately. Moisture can seep in, oxygen can begin oxidizing metal, and ordinary dust and microbes can coat the outer skin. That is why quick recovery matters. When a fall is tracked well, searchers can arrive while the meteorites still look sharp, with a clean fusion crust and minimal staining. In snowy regions, dark stones can stand out clearly, making early finds more likely. Rapid recovery also helps preserve scientific context. Where the pieces land, how they are distributed, and how they match each other can reveal how the object broke apart during flight. Waiting too long can scatter that story. A meteorite is not just a rock to own, it is a record to read, and weather is a slow editor. Finding one quickly keeps the text clear. It lets researchers study a sample that still resembles its space-reveled state, rather than a stone already rewritten by Earth. Fresh meteorites often have a dark fusion crust from surface melting. When a meteorite first reaches the ground, it often looks unlike any ordinary stone nearby. Its surface is coated in a thin, dark crust, formed during its violent passage through the atmosphere. As the outer layer heats rapidly, it melts and flows for only seconds before cooling again once the object slows down. This creates a smooth, glassy skin that seals the interior from air and moisture, at least temporarily. The crust can show subtle ripples or flow lines, frozen evidence of how the air rushed past during entry. Inside, the rock remains largely unchanged, protected by the brief sacrifice of its surface. Over time, weather breaks this crust down, dulling the sharp contrast and making the meteorite harder to recognize. That is why freshly fallen examples are so prized. They preserve a moment of transformation where extreme heat and sudden cooling met in a thin layer you can still see and touch. Some meteorites smell faintly metallic after landing from heated minerals. People who recover meteorites soon after a fall sometimes notice an unusual scent. It is often described as metallic or sulfur-like, and it fades quickly as the stone cools and reacts with air. This smell comes from minerals that were heated intensely during atmospheric entry, then exposed suddenly to Earth's environment. Iron-bearing compounds and sulfides can release volatile components when fractured or freshly oxidized. The effect is subtle and easy to miss, but it is another reminder that the object has just undergone an extreme transition. Space is cold and dry. The lower atmosphere is warm, reactive, and full of oxygen. A meteorite experiences the change in minutes. The scent does not mean the stone is hot or dangerous. It is simply chemistry catching up. As the surface stabilizes, the smell disappears, leaving behind a rock that no longer announces its arrival so clearly. That fleeting detail is one more reason quick recovery matters. Meteorites can carry tiny glassy beads made during violent impact. Inside some meteorites are small rounded beads of glass formed during ancient collisions in space. These beads were once molten droplets created when impacts heated rocks so intensely that it briefly liquefied and sprayed outward. Surface tension pulled the molten material into spheres before it cooled and hardened. The beads then became trapped inside larger bodies, surviving further collisions and long journeys through space. Finding them today is like finding frozen sparks from an ancient catastrophe. Each bead records a moment of extreme energy that happened long before Earth was fully formed. Their size, shape, and composition help scientists reconstruct conditions in the early solar system, including how often collisions occurred and how hot they became. These beads are not decorations. They are physical evidence that violence played a role in building planets. When you see one under magnification, you are looking at the preserved outcome of an impact that happened billions of years ago, locked inside stone that later fell at your feet. Chondrules inside many meteorites formed as molten droplets in early space. Chondrules are small, rounded structures found in many stony meteorites, and they are among the oldest solid materials in the solar system. They formed as droplets of molten rock floating freely in space, cooling rapidly into solid spheres. How they melted so completely remains an active area of research, but their existence shows that early space was not calm or uniform. Short, intense heating events must have occurred. Powerful enough to melt rock, but brief enough to let droplets cool before merging into larger bodies. Over time, these hardened spheres became embedded in growing asteroids, preserved without being fully remelted. When a meteorite breaks open, chondra can appear as small, distinct circles, sometimes visible to the naked eye. They are not random features. Each one is a record of a specific event that happened before planets existed. Holding a conda-bearing meteorite means holding material shaped by conditions no longer present anywhere nearby. Chondrules are older than planets, yet you can hold them today. Before Earth took shape, before oceans formed and continents drifted, chondra already existed. They solidified in the earliest days of the solar system, then waited. Some became part of larger bodies that never went on to form planets. Others were later knocked loose again by subsequent collisions. For billions of years, they stayed mostly unchanged, sealed within parent rocks drifting through space. Earth's own geology has wiped away nearly all traces of its earliest history. But chondrules avoided that recycling by remaining off the planet. When a meteorite containing them lands today, it brings material older than any rock ever formed on Earth's surface. That age is not a guess. It is determined through isotopes that reveal how long these structures have existed. The contrast is remarkable. You can lift a stone from the ground and be holding something that existed before the planet beneath your feet. Chondrules collapse deep time into something tangible, turning abstract age into physical presence. Carbon-rich meteorites contain complex organic molecules found in space. Some meteorites are especially rich in carbon compounds, and their interiors can hold a surprising variety of organic molecules. These include amino acids and other carbon-based structures that form without biology. They assemble through chemical reactions in cold space environments driven by radiation, ice chemistry, and time. When such meteorites fall to Earth, they bring with them a record of chemistry that occurred far from planets and living systems. This does not mean life arrived ready-made. It means the ingredients were forming naturally before planets like Earth were complete. Laboratory studies have shown that these molecules can be diverse and abundant, far more complex than once expected. The meteorite acts as a sealed container, preserving fragile compounds through long travel. Once on Earth, contamination becomes a concern, which is why fresh, carefully handled samples are so valuable. These stones show that organic chemistry is not rare or Earth-specific. It is part of how matter behaves in space. Some carbon meteorites also contain water bound in minerals. Water does not always appear as ice or liquid. In some meteorites, it is locked into the structure of minerals, chemically bound rather than freely flowing. This water formed early when parent bodies interacted with ice and heat, allowing chemical reactions that trapped water inside rock. The result is a solid record of past interactions between rock and water in space. When scientists analyze these meteorites, they can determine how much water was present and how it was incorporated. This has important implications for understanding how water became available on young planets. Rather than arriving all at once, water may have been delivered gradually by many small bodies carrying bound moisture. These meteorites show that water-bearing materials existed long before Earth's oceans. They also show that water can survive extreme conditions when protected inside minerals. A dry-looking stone can contain a hidden history of water, preserved through space travel and atmospheric entry, waiting to be released only in a laboratory. Meteor impacts helped shape Earth's surface, carving craters still visible. Earth's surface carries scars from past impacts, though many are subtle or deeply eroded. When large objects strike, the energy released reshapes the landscape instantly, compressing rock, excavating material, and sometimes melting the ground itself. Over time, erosion, vegetation, and tectonic movement softened these features, but some remain recognizable for millions of years. Impact craters can influence drainage patterns, create basins, and expose deep layers of rock at the surface. They are reminders that Earth's history includes sudden events as well as slow processes. Studying these craters helps scientists estimate how often large impacts occurred and how they affected climate and life. Many craters were not recognized as impact sites until relatively recently. Once diagnostic features were understood, Earth does not advertise its impact history clearly, but it has not erased it completely either. The planet still carries evidence that space has occasionally reached the ground with overwhelming force. The Beringer crater in Arizona came from an iron meteorite impact. This crater is one of the best preserved impact sites on Earth, with a clear rim and scattered debris around it. It formed when an iron meteorite struck the ground at high speed, releasing energy equivalent to a powerful explosion. The impact excavated rock flipped layers upside down and scattered fragments over the surrounding desert. For a long time, the crater's origin was debated, with some suggesting volcanic activity. Eventually, evidence such as shocked minerals and meteoritic iron confirmed its true cause. The site became a turning point in recognizing impact craters worldwide. Unlike many older craters, this one remains sharply defined because of its relatively young age and dry environment. Standing at its edge gives a sense of scale that photographs cannot capture. The crater is not just a hole, it is a snapshot of an instant when space and Earth collided directly, leaving behind a structure that still speaks clearly after tens of thousands of years. Many impact craters are hidden by erosion, forests, oceans, and cities. Earth is active, and that activity works against preserving impact evidence. Rain smooths rims, rivers cut through walls, and vegetation conceals circular outlines. Plate tectonics recycle crust, dragging older surfaces downward and destroying ancient scars entirely. Oceans cover large portions of the planet, hiding any craters formed beneath them. Human development adds another layer, building over structures that once marked violent events. Because of this, the known inventory of impact craters represents only a fraction of those that actually formed. Many more remain undiscovered, their shapes softened beyond easy recognition. Identifying them often requires satellite imagery, gravity measurements, or subtle mineral clues that point to past shock. This hidden history means Earth's encounter rate with large objects is underestimated. If judged only by visible craters, the planet has been struck many times, but it is skilled at hiding the evidence. What remains visible is only what erosion and activity have not yet erased. The Moon's craters preserve a longer meteor history than Earth can. Earth hides most of its early impact history because its surface is constantly changing. Rain, wind, ice, oceans, and moving crust slowly erase old scars. The Moon does not do that. With no atmosphere, no flowing water, and no active plate movement, impacts remain visible for enormous spans of time. New craters simply form on top of older ones, stacking evidence rather than removing it. Some lunar regions are so heavily cratered that almost every new impact lands inside a previous one. By studying crater size and how densely they cover an area, scientists estimate which surfaces are older and how impact rates changed over billions of years. This makes the Moon a reference for understanding how active the early solar system was. While Earth's surface has been reset many times, the Moon has kept its record exposed. Every crater represents a specific collision that would have been erased here but remains preserved there. Meteor impacts on the Moon can still be seen as flashes. The Moon is still being struck by small objects, and some impacts can be observed directly. Without an atmosphere to burn debris into streaks, incoming material reaches the surface intact. When it hits, the energy is released at a single point, briefly heating rock and dust until it glows. To an observer, this appears as a tiny flash on the Moon's dark side that lasts less than a second. Telescopes and sensitive cameras are used to watch for these sudden points of light. Each flash marks a brand new impact, sometimes followed by the formation of a small crater. By recording how often these flashes occur, scientists estimate current impact rates. What makes this striking is timing. You are not seeing an old scar or a distant event. You are watching a collision as it happens on another world. The Moon looks calm and unchanged, yet it is still actively collecting impacts in real time. Spacecraft have recorded meteor impacts on Mars, lighting the thin sky. Mars experiences regular impacts partly because of its location near the asteroid belt and its thinner atmosphere. Some incoming objects break apart, while others reach the surface with enough energy to leave fresh craters. Orbiting spacecraft have detected new impact sites by comparing images taken at different times. These fresh craters often appear with dark blast patterns where dust spreads outward, making them stand out clearly against the surrounding terrain. In some cases, instruments have also recorded atmospheric disturbances associated with meteor entries. Studying these events helps scientists understand how impacts behave on a planet with weaker gravity and less atmospheric protection than Earth. It also allows comparisons between different planetary environments. A meteor that would burn up completely here can reach the ground on Mars. Each new crater becomes a timestamp, marking the moment space interacted directly with the Martian surface. Meteor activity is not unique to Earth. It is a shared process shaping multiple planets at the same time. A meteor can trigger infrasound, a low rumble sensed far away. Large meteors can disturb the atmosphere strongly enough to create infrasound, a type of sound too low in frequency for humans to hear. These pressure waves travel differently than normal sound. They can move vast distances, bending through atmospheric layers, and sometimes traveling across continents. Instruments designed to detect infrasound can register a meteor event long after the visible streak has faded. This allows scientists to confirm powerful fireballs, even when they occur over oceans, remote regions, or at night without witnesses. The strength of the signal can also be used to estimate how much energy the meteor released. What makes this fascinating is the contrast. A meteor can appear silent and feeling, yet still leave a measurable disturbance moving invisibly through the air. The sky briefly behaves like a transmitting medium, carrying information far beyond the original event. The light disappears quickly, but the atmosphere continues to carry the signature of the encounter. Infrasound helps confirm fireballs even when clouds hide them. Cloud cover can completely block the view of a fireball, making it seem as if nothing happened. Infrasound does not care about clouds. When a large meteor passes through the atmosphere, it can generate pressure waves that travel outward regardless of visibility. Infrasound stations around the world continuously listen for these low-frequency signals. When multiple stations detect the same event, scientists can calculate where it occurred and how energetic it was. This makes it possible to confirm fireballs that no one saw and no camera captured. In some cases, infrasound detections are matched with satellite data that recorded a brief atmospheric flash, strengthening the evidence. The process turns the atmosphere itself into a detection system. Even when the sky looks quiet and overcast, it may still be carrying the trace of a meteor event. The fireball does not need witnesses. The air records it automatically and reveals it to those who know how to listen. A meteor's brightness depends on speed, mass, and entry angle. Brightness is not determined by size alone. Speed plays a major role because faster objects release energy more rapidly when they strike the atmosphere. Mass affects how long the meteor can continue glowing before breaking apart. Entry angle shapes the entire display. A shallow angle spreads the interaction over a longer path, while a steep angle concentrates energy into a shorter, more intense burst. The same object entering at a different angle could look completely different from the ground. This is why meteor watching feels unpredictable, even within the same shower. The atmosphere responds to geometry as much as material. Brightness is the visible result of motion, structure, and air density interacting over time. It is not a simple measure of how big the object was. Each meteor represents a unique combination of factors, and the sky displays that outcome briefly before returning to darkness, leaving only memory behind. Shallow entry can produce long, dramatic paths across the sky. When an object enters the atmosphere at a shallow angle, it travels through the upper layers for a longer distance before slowing down. This creates a meteor that can cross a large portion of the sky, sometimes passing through multiple constellations. Because the interaction lasts longer, the light can appear steadier, giving observers time to follow its motion. Shallow entries can also produce gradual brightening and flickering as material is shed in stages. The extended path can make the meteor feel closer than it really is, even though it remains far above the ground. The effect comes from duration, not distance. These long tracks often leave strong impressions because they allow the viewer to observe change rather than just react. A shallow entry turns a momentary flash into a movement with direction and shape. It reveals how a small difference in approach angle can dramatically change what the sky shows, even when the object itself is similar. Steep entry can end quickly in a sudden bright flare. A steep entry sends the meteoroid rapidly into denser air, forcing intense heating over a very short distance. Instead of a long path, the meteor may appear suddenly and vanish just as fast. The rapid stress often causes the object to fragment abruptly, producing a sharp flare near the end of its visible path. This abrupt flare of light can feel explosive, even though it is simply energy being released in a very short span of time. Steep entries allow little pause between the first glimpse and the final flash, which makes them easy to misread. Their brightness and speed can make them seem closer than they truly are. In fact, they still unfold far above Earth's surface. The difference between steep and shallow paths highlights how sensitive meteor behavior is to geometry. A slight shift in angle can transform the same kind of object into either a long, gliding arc or a sudden, intense burst. The atmosphere responds in different ways, and the sky delivers an entirely different display. Fragmentation often splits a single incoming meteoroid into multiple streaks of light. Not all meteoroids stay intact as they enter the atmosphere. Heat and pressure can exploit cracks or weak zones, causing the object to break apart while still moving at high speed. When this happens, the sky may show several streaks traveling together, or a main streak accompanied by smaller branches. Each fragment burns and sheds material slightly differently, creating a complex pattern of light. Fragmentation can also produce sudden pulses of brightness, as fresh surfaces are exposed. These details provide clues about the object's internal structure, revealing that it was not a solid, uniform body. Instead, it may have been loosely bound or mixed in composition. Watching fragmentation unfold turns a single event into a sequence. The meteor becomes something you observe changing, rather than simply appearing and disappearing. The breakup happens faster than analysis, but slowly enough to leave a clear impression of motion, division, and loss before everything fades. Some fireballs break apart explosively, scattering meteorites over wide, strewn fields. When a large fireball fragments deeply in the atmosphere, surviving pieces can separate while still moving quickly. As they slow down, those fragments spread out before falling the rest of the way in darkness. By the time they reach the ground, they can be scattered across a long, narrow area called a strewn field. Larger fragments usually land farther along the path, while smaller ones fall earlier. This pattern reflects how the object broke apart and how winds influence the final descent. Searchers use these patterns to guide recovery efforts, turning a sky event into a ground investigation. A single fireball can therefore produce many meteorites, each representing a different part of the original object. Recovering multiple pieces allows scientists to compare them, revealing differences between interior and exterior material. The fireball is the visible moment. The strewn field is its physical outcome, connecting a flash in the sky to a distribution of stones on the ground. A strewn field is an elongated zone where meteorites land after breakup. When a meteoroid breaks apart in the atmosphere, the story does not end with the fireball fading. The remaining fragments are still moving forward at high speed, even as air resistance slows them rapidly. This creates a landing pattern stretched along the original flight path, rather than a single impact point. Larger fragments tend to travel farther before falling, while smaller pieces lose momentum sooner and drop earlier. Winds at different altitudes can spread lighter fragments sideways during their final descent, subtly reshaping the pattern on the ground. The result is a long, narrow zone where meteorites may be found, sometimes extending for many kilometers. Scientists use this pattern to reconstruct how the object fragmented and how deeply it penetrated before breaking apart. Each recovered stone becomes a data point. Together, the pieces reveal the invisible final moments of the object's passage, turning a brief flash in the sky into a measurable event written across the landscape. Iron meteorites are rarer than stony ones, yet easier to notice. Although most meteorites are stony, iron meteorites often attract attention because they behave differently from ordinary rocks. They are much denser than they appear, making even small pieces feel unexpectedly heavy when lifted. Their metallic nature allows them to survive weathering longer than many stony meteorites, which can crack or blend into surrounding geology over time. Many iron meteorites also show distinctive surface features formed during atmospheric entry, including smooth curves and shallow depressions created as material was stripped away unevenly. When cut and polished, their interiors can display striking metal structures that formed during extremely slow cooling inside a larger parent body. These structures do not form under normal surface conditions on Earth. Historically, iron meteorites were valuable sources of workable metal long before smelting was common. Their rarity in nature and durability on the ground make them more likely to be found, remembered, and preserved once discovered. Many meteorites are found in Antarctica, preserved on ice and easy to spot. Antarctica is one of the most productive places on Earth for recovering meteorites. Not because more fall there, but because the environment preserves and concentrates them. Dark stones stand out clearly against pale ice, making visual searches far more effective than in vegetated regions. Cold temperatures slow chemical alteration, allowing meteorites to remain recognizable for long periods. Ice movement also plays a crucial role. Flowing glaciers carry embedded rocks and gradually expose them in areas where surface ice is removed by wind and sublimation. These blue ice zones act as natural collection sites where meteorites from many different falls accumulate. Researchers can search these regions systematically, often recovering numerous samples in a small area. Each find is carefully documented because the surrounding ice tells part of the transport story. With minimal soil, vegetation, and human debris, Antarctica offers a rare setting where meteorites can remain clean, visible, and scientifically valuable long after they arrive. Deserts also concentrate meteorites, where dark stones stand out. Hot deserts provide another environment where meteorites can survive and be found more easily than in wetter climates. Sparse vegetation means fewer places for rocks to hide, and slow soil formation keeps stones exposed near the surface for long stretches of time. In many desert regions, light-colored ground contrasts strongly with dark meteorites, especially those retaining a fusion crust or unusual shape. Wind erosion can remove fine dust and leave behind stable gravel plains where meteorites remain visible instead of being buried. Dry conditions also slow some chemical reactions, allowing meteorites to keep identifying features longer than they might elsewhere. These factors have made deserts important sources of recovered meteorites worldwide. The challenge is that deserts also contain deceptive look-alike rocks, including volcanic stones and industrial debris. Because of this, careful documentation and later testing are essential. Even so, deserts increase the odds that a meteorite remains visible long enough to be noticed and studied, rather than disappearing unnoticed into the ground. Meteorites can be mistaken for slag, so laboratories confirm them carefully. Many objects that look convincing at first glance turn out not to be meteorites at all. Industrial slag can appear dark, dense, and oddly shaped, closely mimicking features people associate with space rocks. Some volcanic materials can also display glassy surfaces, bubbles, or metallic-looking grains. Because of this, visual inspection alone is unreliable. In laboratories, scientists examine internal textures and mineral composition using microscopes and chemical analysis. Real meteorites often show specific structures such as chondrules or distinctive metal grain arrangements that are difficult for Earth materials to replicate accurately. Chemical testing can reveal element ratios that differ from industrial or natural terrestrial sources. Classification goes beyond simply confirming authenticity. It places the meteorite into a known group, linking it to formation processes and parent bodies. This careful approach prevents collections from filling with misidentified material and ensures that each accepted specimen adds meaningful scientific information rather than confusion or noise. A magnet can hint at meteorite metal, but many Earth rocks fool magnets. Using a magnet is a common first test, but it can be misleading in both directions. Many meteorites contain iron-rich metal and will respond to a magnet, but many Earth rocks also attract magnets because they contain magnetite or other iron-bearing minerals. Industrial slag is especially deceptive and is one of the most frequent sources of false positives. At the same time, not all meteorites show a strong magnetic response. Some stony meteorites contain only small metal grains, producing a subtle attraction that is easy to underestimate. This leads to two common errors: accepting the terrestrial rock because it is magnetic, or rejecting a real meteorite because the pole seems weak. Magnetism is therefore best treated as a preliminary clue rather than a deciding test. Reliable identification depends more on density, texture, internal structure, and chemical composition. A magnet can spark curiosity, but confirmation requires evidence that goes far beyond the simple attraction test. True meteorites often have nickel-rich iron, uncommon in most surface rocks. One of the most reliable chemical indicators of meteoritic origin is the presence of metallic iron that contains significant nickel. On Earth's surface, native iron metal is rare because oxygen and moisture quickly convert it into rust and other compounds. When metallic iron does occur naturally, it usually lacks the nickel levels commonly found in meteorites. In meteoritic metal, nickel is not incidental. It reflects slow cooling and separation processes that occurred inside parent bodies in space. Measuring nickel content helps distinguish real meteorites from industrial iron, slag, or terrestrial minerals that may look similar. This information also aids classification, revealing whether the meteorite came from a differentiated body with a core or from more primitive material. Because nickel levels are difficult to fake naturally on Earth, even the tiny metal grain can be decisive. A stone that appears ordinary externally can contain internal evidence that firmly places its origin beyond our planet. Some meteorites come from the Moon, blasted off by impacts. Lunar meteorites begin with powerful impacts on the Moon, but eject rock fragments fast enough to escape lunar gravity. Because the Moon's gravity is weaker than Earth's, and there is no atmosphere to slow debris, some material can be launched directly into space. Most of these fragments travel around the Sun for long periods, but a small fraction eventually intersects Earth's orbit. When they enter our atmosphere, they arrive like any other meteorite fall. Scientists identify lunar meteorites by matching their mineral chemistry and isotopic signatures to known lunar samples and remote measurements of the Moon's surface. These meteorites are valuable because they can come from regions never visited by spacecraft. Many are brexers, formed from shattered material fused by repeated impacts, reflecting the Moon's heavily cratered history. Each lunar meteorite expands our understanding of the Moon beyond limited landing sites, delivering direct samples of another world through natural processes alone. Others come from Mars, identified by trapped gas matching Martian air. Some meteorites are confirmed as Martian because they contain tiny pockets of gas sealed inside minerals or impact glass. When analyzed, these gases match the composition of the Martian atmosphere, measured by spacecraft. This match provides a strong link between the rock and its planetary origin. The journey begins with a major impact on Mars that launches near-surface rock into space at extreme speed. A few fragments survive ejection and long exposure to radiation before eventually crossing Earth's path. Once recovered, these meteorites allow laboratory studies that cannot be performed remotely. Scientists can examine minerals, dates, and shock features with great precision. These stones retain records of volcanic processes, collision events, and chemical environments on Mars from long before they departed that world. The discovery of trapped atmospheric gases makes the link unmistakable. It allows a rock recovered on Earth to be confidently connected to the air and surface of another planet. To hold a Martian meteorite is to hold a fragment of another world. It is not symbolic. It is a tangible object formed under Martian conditions, preserving a history unique to that planet. It began within the Martian crust, underwent Martian geology, and then endured a violent ejection, a long passage through space, and finally, entry through Earth's atmosphere. That sequence of events is rare, which is why these meteorites are uncommon and carefully studied. In laboratories, scientists can slice them thin, analyze mineral structures, and read chemical records locked inside crystals. These analyses reveal cooling histories, impact pressures, and alterations that occurred before the rock ever left Mars. The information complements rover and orbiter data by providing material that can be examined directly. The significance comes from tangibility. Mars is no longer just an image or a distant landscape. In this case, it is weight, texture, and structure held in your hand. Distance collapses into something physical, immediate, and undeniably real. Some meteorites come from the asteroid Vesta, based on spectral matches. Scientists have been able to trace certain meteorites back to a specific asteroid, rather than a general region of space. Vesta is large, bright, and well-studied, and its surface reflects sunlight in a way that creates a distinctive spectral signature. When researchers compared that signature with meteorites found on Earth, the match was remarkably close. This suggested that impacts on Vesta blasted material into space, some of which later crossed Earth's orbit. Vesta also shows enormous impact scars, making the ejection of debris physically plausible. These meteorites reveal that Vesta once experienced volcanic activity and internal heating, giving it a layered structure more complex than many asteroids. Holding one of these meteorites means holding a fragment of an object whose surface we have mapped from space. It is a rare case where telescopic observation and a rock in your hand can be directly connected, turning an asteroid from a distant point of light into a known source. Meteor streams slowly shift as planets tug their dust with gravity. Meteor streams are not fixed highways in space. They are loose collections of particles that respond to gravity over time. As planets orbit the Sun, their gravitational pull gently alters the paths of these dust streams, stretching them, bending them, and shifting them bit by bit. These changes happen slowly, but over centuries they become significant. A stream that once produced frequent meteors can thin out or drift away from Earth's orbit. In other cases, gravity can push denser parts of the stream closer, increasing activity long after the parent object has passed. This is why meteor showers are not permanent in their strength. They evolve as the solar system moves. Studying these gradual shifts helps scientists predict how showers may change in the future. What feels like a stable yearly event is actually the result of long-term gravitational nudges acting on fragile trails of dust. Jupiter's gravity can sculpt meteor streams, boosting or dispersing future showers. Jupiter's immense gravity makes it one of the most powerful influences on meteor streams. When a stream passes near the giant planet, its particles can be pulled into new configurations. Some sections may be compressed into dense filaments that later produce intense meteor displays on Earth. Other sections may be stretched or scattered, weakening or even eliminating future activity. These encounters often happen long before Earth ever crosses the stream. As a result, a shower's behavior can change dramatically without any new material being added. Jupiter's influence helps explain why some showers suddenly surge or fade across historical timescales. The night sky reflects these ancient gravitational encounters. A meteor streak seen today may owe its existence to a close approach with Jupiter centuries ago. In this way, the planet acts as both a sculptor and a disruptor, quietly reshaping the paths of dust that later become familiar events in Earth's sky. A meteor shower's best display can change across centuries. Meteor showers are often treated as dependable yearly events, but their intensity is not fixed forever. The dust streams that caused them evolve as gravity, radiation, and planetary encounters reshape their structure. Over centuries, Earth's path through a stream can shift relative to its densest regions. A shower that was once spectacular may fade into modest activity, while another can grow stronger after long periods of quiet. Historical records show that some famous showers produced dramatic outbursts in the past that are rare or absent today. These changes are not random. They reflect how dust, released at different times, spreads out and moves under gravitational influence. This means meteor showers have long memories tied to the past behavior of their parent objects and the planets they encounter. Watching a shower today is like seeing one frame of a very long process. The sky you see now is not guaranteed to be the sky people saw centuries ago. Even on the same calendar date, the same shower looks richer after midnight because Earth faces forward. Then the timing of meteor showers is closely tied to Earth's motion through space. After midnight, an observer's location on Earth rotates into the direction the planet is moving along its orbit. This means the atmosphere is effectively facing into the incoming dust stream rather than trailing behind it. As a result, more particles encounter the atmosphere head-on, increasing the number of visible meteors. Before midnight, Earth's rotation places you on the trailing side, where fewer particles are encountered. This is why many experienced observers recommend watching after midnight for better results. The change has nothing to do with the shower itself becoming stronger. It is purely about geometry and motion. You are turning into the flow rather than away from it. Understanding this makes meteor watching feel less mysterious and more connected to Earth's movement. A Earth's rotation quietly determines when the sky is most likely to light up. Your latitude changes what showers you can see due to radiant height. Where you live on Earth affects which meteor showers you can see. Well, each shower has a radiant point in the sky, and its height above the horizon depends on your latitude. If the radiant stays low or never rises, many meteors will be hidden by the horizon. If it climbs high, more of the sky becomes available for long streaks. This is why some showers favor northern observers, while others are better viewed from the south. Even for the same shower, viewing conditions can differ dramatically between locations. A strong display in one hemisphere may appear weak or non-existent in another. Latitude also affects how long the radiance stays visible each night. Understanding this helps set realistic expectations. It explains why reports from different parts of the world can sound so different for the same event. The shower itself has not changed. The viewing geometry, as the moon's brightness can wash out faint meteors, changing the experience. Moonlight has a powerful effect on meteor watch. When the moon is bright and high in the sky, its light raises the background brightness, making faint meteors harder to see. The result is not that fewer meteors occur, but that fewer are detected by the eye. Bright fireballs still stand out, but subtle streaks disappear into the glow. This can make an active shower feel disappointing, even when conditions in space are favorable. Observers often plan sessions around moon phases, choosing times when the moon sets thoroughly or rises late. Positioning also matters. Keeping the moon behind you or blocked by terrain can improve visibility. Understanding the moon's role helps manage expectations and avoid false conclusions about a shower's strength. The sky is still active, but your visual threshold has changed. Moonlight does not stop meteors. It simply hides the quieter ones. Dark adaptation matters. Your eyes need time to become more sensitive. Human eyes do not reach full night sensitivity instantly. After exposure to light, it can take many minutes for vision to adjust to darkness. During this time, faint meteors are easy to miss. Bright screens, flashlights, or nearby lights can reset this process quickly. Experienced observers protect their night vision by avoiding direct light and allowing time for adaptation. As sensitivity improves, the sky appears richer, revealing dim stars and subtle streaks that were invisible before. This change can feel dramatic. The same sky can seem empty at first, then gradually fill with detail. Dark adaptation does not increase meteor activity. It increases your ability to notice what is already happening. Understanding this can transform the experience from frustrating to rewarding. Patience becomes part of the observation. The longer you allow your eyes to settle into darkness, the more the sky gives back. Meteors can appear anywhere, but showers increase odds in predictable windows. Sporadic meteors can appear in any part of the sky on any night, but meteor showers raise the odds by concentrating activity into specific times. During a shower, Earth passes through a known dust stream, increasing the number of particles entering the atmosphere. This does not guarantee constant activity, but it makes meteors more frequent than average. The key advantage is predictability. Showers return at roughly the same times each year, allowing observers to plan sessions instead of relying on chance. Even then, activity fluctuates. Short bursts can be followed by quiet periods. Understanding this helps set expectations. A shower is not a continuous display. It is an increase in probability. Knowing when Earth crosses these streams turns random sky watching into a timed opportunity, where patience and preparation are rewarded more often than on ordinary nights. A shower's peak is brief because Earth crosses the densest part quickly. Meteor streams are not uniform clouds. They often contain dense cores surrounded by thinner regions. As Earth moves through a stream, it spends a mere short time crossing the densest section. This produces a peak that may last hours rather than days. Before and after the peak, activity can still occur, but at lower rates. The brevity of the peak explains why timing matters so much. Missing it can mean seeing only a fraction of the shower's potential. The exact timing can vary slightly from year to year as streams shift, which adds uncertainty. Still, predictions are usually accurate enough to narrow the window. This structure also explains why reports can differ sharply between observers on the same night. Someone watching at the right moment may see a surge, while others see little. The shower is not fading randomly. Earth has simply passed beyond the densest section of the stream and entered a quieter region of space. Sporadic meteors are random and are not associated with any named shower. Most meteors seen on typical nights do not belong to a well-known display. They are called sporadic because they arrive from unpredictable directions without a common radiant or reliable schedule. These particles come from debris spread throughout the inner solar system, left behind by many different sources over vast stretches of time. Because they are not gathered into defined streams, they cannot be predicted the way meteor showers can. A sporadic meteor may appear anywhere in the sky at any hour on any clear night. This unpredictability is why even casual observers sometimes witness a meteor when no shower is underway. Sporadic meteors also tend to have a wider range of speeds and appearances, reflecting their mixed origins. They form a constant background level of activity that never fully stops. Even when the calendar looks empty, Earth is still encountering stray materia. The sky may feel quiet, but it is never inactive. Sporadic meteors are more common than shallow meteors on many nights. Outside major SHA peaks, sporadic meteors usually outnumber SHA members. Earth spends far more time moving through diffused debris than through dense comet streams. This means that on a typical clear night, most visible meteors are unrelated to any named event. They appear singly, spaced out in time, often surprising the observer. Because they come from many directions, they do not create patterns or bursts that draw attention. This can make the sky feel quieter than it really is. During weaker showers, sporadic meteors can still dominate what people actually see. This explains why reports often differ even when observers watch at the same time. One person may notice a few isolated streaks, another none at all. Sporadic activity is steady but subtle. It does not announce itself with peaks or schedules. Instead, it represents the everyday level of interaction between Earth and scattered material drifting through space. Some meteors are Earth grazers that skim the atmosphere and escape again. A small number of meteors follow paths that barely dip into the atmosphere. These are Earth grazers. They enter at very shallow angles, encountering enough air to glow briefly without losing enough energy to fall. Instead of plunging downward, they skim along the upper atmosphere and then continue back into space. The heating comes from their high speed and light contact with thin air, not from deep penetration. After this brief interaction, the object escapes Earth's gravity and resumes orbiting the Sun. Earth grazers are rare because the entry angle must be extremely precise. Too steep, and the object burns up. Too shallow, and it misses the atmosphere entirely. When they do occur, they often produce unusually long, slow streaks that seem to slide across the sky. They are reminders that not every shooting star ends on Earth. Some only pass by, leaving light behind and nothing else. Earth-grazing meteors can travel hundreds of kilometers while still glowing. Because Earth grazers enter at such shallow angles, they can remain within the glowing region of the atmosphere for a very long distance. Instead of a short streak, they may trace paths hundreds of kilometers long. Observers far apart can witness the same event from different locations, each seeing a different section of the glowing track. The light persists because the meteoroid stays within thin atmospheric layers where heating happens gradually. This produces slow, extended displays that last several seconds. Despite how dramatic they look, these meteors are still extremely high above the ground. The sense of scale comes from distance traveled, not closeness. These events are especially memorable because they give the eye time to follow motion and direction. They show how strongly entry angle controls meteor behavior. A small change in trajectory can transform a brief flash into a sweeping arc that crosses regions and links distant observers through a single event. A few meteoroids get captured briefly, becoming temporary tiny moons. On rare occasions, a small object passing near Earth loses just enough energy to become temporarily trapped by gravity. Instead of falling or escaping immediately, it enters a short-lived orbit around the planet. These objects are sometimes called temporary moons or mini-moons. Their capture periods are brief, often lasting months before they drift away or re-enter the atmosphere. Because they are small and faint, most are detected only by dedicated surveys. Their existence shows that Earth's gravitational influence is not a sharp boundary. Objects can move in and out of capture, depending on speed and approach angle. While orbiting, these tiny moons follow irregular paths shaped by Earth, the Moon, and the Sun. They are not stable satellites, but passing companions. Their discovery adds depth to our picture of near-Earth space. The region around the planet is active and dynamic, with objects occasionally pausing before continuing on their way. The atmosphere protects life by destroying vast amounts of incoming debris. Earth's atmosphere acts as a protective barrier against constant bombardment from space. As particles enter, air resistance forces them to release energy high above the surface. Most incoming debris vaporizes completely, never reaching the ground. Even larger objects are often broken apart or slowed significantly before impact. Without this process, Earth would experience far more frequent and damaging strikes. The familiar sight of a shooting star is evidence of this protection working as intended. Each streak marks material that has been intercepted and neutralized. Over long periods, this shielding has shaped Earth's environment by limiting how much extraterrestrial material reaches the surface intact. It allows life to exist without constant disruption. What looks like a brief flash is actually part of a continuous defense. Night after night, the atmosphere absorbs energy and matter from space, quietly preventing countless small impacts that would otherwise accumulate. The sky light show is a sign of safety, not danger. Earth sweeps up tens of tons of space material each day. As Earth moves along its orbit, it continuously encounters material drifting through the inner solar system. This includes microscopic dust, sand-sized grains, and occasional larger fragments. Over a single day, the total mass adds up to tens of tons. Most of this material enters gently, or is too small to produce visible meteors. Instead, it slows gradually and settles through the atmosphere. Although this added mass is tiny compared with Earth itself, the process never stops. Of the long timescales, it contributes measurable amounts of extraterrestrial material to the planet's surface. This steady input shows that Earth is not isolated from its surroundings. It is constantly interacting with leftover debris from formation and collisions elsewhere. Space is not something we pass through occasionally. We are always moving within it, collecting small pieces as we go. The planet grows very slowly from material that once orbited the Sun independently. Much of that material becomes microscopic dust that settles quietly everywhere. Most incoming space material arrives not as dramatic fireballs, but as microscopic particles. These grains lose speed high in the atmosphere and drift downward over time. They eventually settle onto land, oceans, ice, and rooftops without drawing attention. Mixed with earth dust, they become part of soils, sediments, and snow layers. In clean environments, scientists can isolate these particles and identify their extraterrestrial origins through composition and structure. Unlike meteorites, this dust does not announce itself. Its arrival is silent and continuous. Over long periods, it accumulates in measurable amounts, spreading traces of space across the planet. Even in remote places, microscopic fragments from asteroids and comets can be found embedded in natural surfaces. This quiet process is one of the most constant ways Earth interacts with space. The connection is not occasional, it is ongoing, subtle, and nearly everywhere. Meteor dust contributes iron to oceanally feeding plankton in some regions. When cosmic dust settles into the ocean, it becomes part of marine chemistry. Some of this dust contains iron, an element required by many types of plankton. In regions where iron is scarce, even small additions can influence biological activity. As the dust dissolves, it releases trace nutrients that plankton use to grow, supporting the base of marine food webs. This connection links events in space to life in Earth's oceans in a quiet way. The effect is gradual and spread over large areas rather than dramatic or local. Scientists study ice cores and ocean sediments to understand how variations in dust delivery may have influenced past ecosystems. Meteor dust is not the only source of iron, but it is one contributor among several. Its importance lies in showing that extraterrestrial material can play a role in Earth's systems without leaving obvious marks. Space adds not just spectacle, but ingredients. Shooting stars are one reason we can find cosmic material in ring water. When meteors burn up, they release vaporized material into the upper atmosphere. Over time, these atoms and tiny particles mix with air and eventually become incorporated into precipitation. Rain and snow can carry trace amounts of extraterrestrial material to the surface. This does not mean rainwater is full of space dust, but it does mean that some cosmic material returns in dissolved or microscopic form. Scientists have detected isotopic signatures in rain and ice that point to non-ear origins. This shows that the atmosphere acts as a mixing layer between Earth and space. A meteor does not need to leave a stone on the ground to matter. Even when it vanishes completely, its material can still cycle back. The process is slow and subtle, but it is continuous. Each shooting star adds a tiny contribution, and over long periods, those contributions become measurable in the water that falls back to Earth. Early scientists debated meteors because rocks from the sky sounded impossible. For centuries, educated thinkers rejected the idea that stones could fall from space. The prevailing view held that the heavens were perfect and unchanging, while rocks belonged strictly to Earth. Reports of fiery objects and falling stones were often explained away as lightning strikes, volcanic ejecta, or superstition. Even when physical samples were presented, scholars argued they must have formed on the ground after impact. The problem was not a lack of observations, it was a conflict with accepted models of nature. Accepting meteorites meant accepting that Earth was not isolated from space. This challenged deep assumptions about how the universe worked. As a result, eyewitness accounts were ignored or dismissed even when they were numerous and consistent. The debate shows how strongly ideas can shape interpretation. Evidence alone was not enough. Scientific frameworks had to change first before rocks from the sky could be taken seriously. A famous meteorite fall at Lel helped convince skeptics in the 19th century. In the early 19th century, a dramatic meteorite fall near La Relle in France forced a shift in scientific opinion. After a bright fireball was seen, thousands of stones were reported to have fallen across a wide area. What made this event decisive was the investigation. A respected scientist interviewed witnesses, mapped where stones were found, and examined the material itself. The fragments were chemically distinct from local rocks and were scattered in a clear fall pattern. The evidence connected the fireball directly to the stones on the ground. This was difficult to dismiss as coincidence or folklore. The Largo 4 did not introduce new ideas. It organized existing observations into a coherent case. Afterward, rejecting meteorites became harder than accepting them. The event marked a turning point, showing that careful documentation could overturn long-held assumptions about the separation between Earth and space. Cultures worldwide recorded meteor showers, sometimes linking them to omens and calendars. Long before modern astronomy, people around the world carefully watched the sky. Meteor showers were recorded in chronicles, oral histories, and early calendars. Because they appeared suddenly and dramatically, they were often interpreted as signs or warnings. Some cultures linked them to political change or natural disasters. Others used their regular appearances to mark seasons or ceremonial times. These records were not scientific explanations, but they were consistent observations. Descriptions of skies filled with falling stars appear across continents and centuries. Today, researchers compare these accounts with modern calculations of meteor shower cycles. In many cases, the dates align closely. This shows that careful observation existed long before understanding. Cultural interpretations varied, but the events themselves were real and repeatable. These records preserved knowledge across generations, quietly documenting Earth's repeated encounters with streams of cosmic debris long before their true origin was known. The Leonid storm of the 19th century stunned observers across North America. During the 19th century, a Leonid meteor storm created one of the most powerful displays ever documented. Witnesses across North America reported meteors appearing in astonishing quantities, far exceeding those of ordinary showers. Descriptions spoke of almost unbroken streaks filling the sky for hours on end. The magnitude of the event stunned both the public and the scientific community. It became evident that this was not random behavior. The timing aligned with earlier historical accounts of similar outbursts, pointing to a repeating event. That insight led researchers to look for an organized source, rather than atmospheric explanations. The storm became a turning point, helping shift meteor science toward orbital interpretations. It demonstrated that Earth was passing through dense regions of space debris. The Leonid storm did more than impress observers. It forced a rethinking of how meteors behaved and why some years produced displays far more intense than others. Modern cameras can capture meteor spectra, revealing elements in the glowing gas. When a meteor enters the atmosphere, its light carries chemical information. Modern cameras, equipped with spectral tools, can separate that light into distinct colors. Each color corresponds to specific elements being excited during entry. By analyzing these patterns, scientists can identify metals such as sodium, iron, and magnesium without recovering a physical sample. Spectra also reveal which light comes from the meteoroid itself and which comes from atmospheric gases. This allows detailed study of composition from brief events lasting only seconds. Different meteors show different spectral signatures reflecting varied origins. A single streak becomes a chemical record captured in real time. This technique turns the sky into a laboratory where high-speed interactions reveal their ingredients instantly. Even meteors that completely vaporize can still provide valuable information, preserved not in stone, but in light, recorded by sensitive instruments. High-speed cameras show meteors flicker as they tumble and fragment. To the unaided eye, a meteor often appears smooth and continuous. High-speed cameras reveal a different story. Many meteors flicker, pulse, or change brightness rapidly as they travel. This behavior reflects tumbling, uneven heating, and fragmentation. As different surfaces are exposed, material sheds at varying rates. Small pieces may break away, briefly flaring before vanishing. Capturing this motion frame by frame allows scientists to infer shape, strength, and internal structure. A steady glow suggests cohesion, while rapid flickering often indicates weakness. These observations show that meteors are dynamic objects responding to intense forces. Each flicker contains information about how materials behave under extreme stress. What looks simple to the eye is actually complex and changing. High-speed footage transforms a fleeting streak into a detailed physical experiment recorded in light. Some meteors create persistent trains that twist as upper winds shear them. After some bright meteors fade, a faint glowing trail remains in the upper atmosphere, These persistent trains can last minutes rather than seconds. They are made of ionized gas and fine particles left along the meteor's path. High-altitude winds begin to act on the trail, stretching and distorting it over time. What starts as a straight line can bend, curl, or ripple as different layers of air move at different speeds. Observers sometimes watch these changes unfold gradually. Persistent trains offer a rare way to visualize winds at altitudes that are otherwise difficult to study. The meteor itself is gone, but its path remains briefly visible. These lingering traces turn an instant event into an evolving display, revealing atmospheric motion normally hidden from view. Upper atmosphere winds can distort those trains into spirals within minutes. The upper atmosphere contains winds moving in different directions and speeds at different heights. When a persistent meteor train forms, it becomes a visible tracer within these layers. As time passes, wind shear pulls parts of the trail apart, twisting it into curves or spirals. These changes can happen quickly, sometimes within minutes. Watching this distortion provides insight into how energy and motion move through the upper atmosphere. The transformation can be striking, turning a straight line into a complex shape. For scientists, this offers a natural experiment. For observers, it extends the meteor experience beyond the initial streak. The sky briefly reveals motion that is usually invisible, showing that even at great heights, Earth's atmosphere is active and structured. Meteors can be photographed from airplanes above clouds, revealing hidden displays. From the ground, clouds often block meteor activity entirely. From an airplane, the situation can be very different. Flying above weather systems places observers closer to clear skies. Cameras positioned near windows have captured meteors streaking below the aircraft, lighting cloud tops or glowing against darker air. This perspective reveals activity invisible from the surface. Reduced light pollution at cruising altitude can also improve contrast, making faint events easier to detect. Aircraft cover large distances quickly, increasing the chance of capturing rare events. These observations show that meteor activity does not stop when clouds roll in. It continues above them, unnoticed by those below. Airborne views remind us that the sky is layered, and that what appears quiet from the ground may still be active just out of sight. The International Space Station sometimes sees meteors below, flashing in Earth's airglow. Astronauts aboard the International Space Station occasionally observe meteors from orbit. From this vantage point, the streaks appear below them, flashing within the thin atmosphere against Earth's airglow. The view reverses the usual perspective. Instead of looking up, they look down on the interaction between space debris and air. These observations show how high most meteors occur, far above clouds and weather. They also reveal how brief and localized the light really is. Seen from above, a meteor is a quick spark along a vast curved horizon. This perspective reinforces that meteors are atmospheric events, triggered by space material. They belong to the boundary between Earth and space. Even from orbit, the planet's thin protective layer is clearly visible, lighting up momentarily as it absorbs incoming debris. A meteor's true path is three-dimensional, yet your eyes see a flat streak. Your eyes see a meteor as a line drawn on the dome of the sky. But the real motion is a three-dimensional track through a deep layer of atmosphere. That difference matters because it explains why direction and distance feel so confusing. A meteor moving toward you can look short and slow, even if it is fast, because most of its motion is hidden in depth. One moving sideways across your view can look long and dramatic because you see more of the track projected against the stars. This is also why two people can describe the same meteor differently. From one town, it may appear near the horizon, while from another, it may look overhead. Even though the path in space was the same, cameras from different sites can combine their views to reconstruct the full trajectory. The meteor was never a flat line. Your view was. Bright meteors can cast shadows, proving how intense their light can be. Most meteors are too faint to affect the ground, but a powerful fireball can momentarily light the landscape like a distant flashbulb. People have reported seeing trees, fences, and rooftops throw brief moving shadows, even on moonless nights. That is a useful clue because it shows the meteor's brightness was not just impressive against the stars, it was strong enough to compete with the darkness around you. In some recorded events, security cameras capture the ground brightening and dimming as the fireball flares. The shadow may shift because the meteor is moving while it shines, changing the direction of illumination in seconds. This effect also helps explain why some fireballs feel close even when they are high in the atmosphere. Your environment responds, and your brain treats that as proximity. A shadow is physical evidence that the light reached the ground with real intensity. The sound delay after a fireball can reveal its distance and height. A bright fireball can be seen instantly, but if it produces sound, that sound arrives later. The delay is not mysterious. Light reaches you almost immediately, while sound must travel through air. If you count the time between the flash and the first boom or rumble, you are measuring distance through the atmosphere. A long delay suggests the event happened far away or high overhead. A shorter delay suggests it occurred closer or that part of the breakup happened lower. Some fireballs produce multiple sounds because fragmentation can occur in stages, creating separate pressure waves that arrive at different times. This makes the experience feel strange, as if the sky is answering late. Scientists use these delays alongside camera data and infrasound records to refine trajectories. For an observer, the delay turns a moment of light into a measurable clue. The sky is not just putting on a show, it is providing timing information you can feel. Some meteoroids are fragile comet dust, others are tough asteroid fragments. Not all incoming material is built the same. Some meteoroids are porous and fragile, especially those shed from comets. They can crumble easily and burn up high, producing soft, brief streaks that vanish without drama. Others come from asteroids and can be denser and stronger, sometimes containing solid rock or metal that holds together longer under stress. This difference shapes what you see. Fragile material may create a faint meteor that ends quickly. Tougher material can survive deeper and may flare as it breaks apart under increasing pressure. The same shower can include both types because debris streams mix particles of different sizes and strengths. This variety is why meteor watching never feels identical from one night to the next. You are not only seeing speed, you are seeing material properties expressed as light. Each meteor reveals something about the object's structure. Even though the object itself is usually destroyed, the atmosphere becomes a testing ground that separates fragile from tough in seconds. Tougher meteoroids can penetrate deeper before breaking apart. As a meteoroid descends, the air grows denser and the forces intensify quickly. A strong, compact object can resist that stress longer, maintaining its integrity into lower layers where the heating is harsher. This is why some bright meteors appear to keep going long after you expect them to fade. They are not simply bigger. They are structurally able to endure deeper passage. Deeper penetration also increases the chance of dramatic fragmentation because the stresses rise steeply and failure can be sudden. It can also increase the chance that a surviving fragment becomes a meteorite, since the object has remained intact long enough to slow and transition into dark flight. Observers sometimes notice these meteors ending with a bright flare low in the sky. That low endpoint is a hint that the body stayed together longer than most. Toughness becomes visible. The atmosphere is gradually applying pressure, and the object is revealing how long it can hold. Very slow meteors can look almost gentle because they excite less air. Speed controls how rapidly energy is transferred to the atmosphere. A slow meteor enters with less kinetic energy per moment of flight, so the heating and excitation of air can be weaker and more gradual. The result can look calmer. The streak may be dimmer sometimes, with a softer appearance, and it may seem to drift rather than snap across the sky. Slow meteors are often easier to track with your eyes because they give you more time to follow their motion. They can also show subtle color or changes in brightness that are easy to miss in faster events. Slow does not mean harmless or small. It means the interaction is stretched out and the atmosphere responds less violently. These meteors remind you that the same basic process can produce very different experiences. A shooting star is not one kind of event. It is a range of encounters shaped by entry speed. When a slow one appears, it feels like the sky is letting you watch the physics unfold instead of flashing past too quickly to register. Very fast meteors can look sharp and sudden because they burn rapidly. A fast meteoroid delivers energy to the atmosphere extremely quickly. Air in front of it is compressed and heated intensely, and the object can ablate so rapidly that the visible event is short and crisp. This is why some meteors look like instant cuts of light appearing and disappearing before you can react. The brightness can rise suddenly, especially if the object fragments and exposes fresh surfaces. Fast meteors often leave a strong impression because they feel decisive. There is little time to track them, so the mind records a single, sharp moment. Their speed also affects where they become visible, since intense heating can begin higher up and reach peak brightness quickly. In meteor showers known for high velocities, this sharpness becomes part of the shower's character. Watching a very fast meteor is like seeing an extreme transfer of energy played out in a second. The atmosphere responds violently, and then everything is over. The sky returns to normal as if nothing happened. Meteor showers let you sample a comet's history without leaving Earth. A meteor shower is not random. It happens when Earth crosses a stream of debris laid down by a parent body over repeated passages around the Sun. The cometary shower, that debris, is a record of the comet shedding material each time it heats up near the inner solar system. Different parts of the stream can contain particles released at different times, which means a shower is like encountering multiple chapters of the comet's past. You do not need to visit a comet to interact with its material. Earth's orbit brings the material to the atmosphere on schedule. The meteors you see are tiny pieces of that trail, burning up and revealing their presence through light. Some showers change over time because gravity shifts the stream, but the core idea remains. You are crossing a path the comet carved. A shower is a natural sampling event where orbital mechanics deliver fragment to your sky. It turns distant solar system history into something visible from a backyard. Every shooting star is a tiny experiment in physics happening in real time. In a few seconds, a meteor demonstrates extreme speed, intense heating, and rapid material loss. A solid object enters the atmosphere. Air compresses in front of it, and energy is converted into light. The exact outcome depends on factors you can sometimes infer from what you see. A long path suggests a shallow entry. A sudden flare suggests fragmentation. A change in color hints at different materials vaporizing. Even the fading can tell a story, because some trails linger as the atmosphere recombines and cools. Unlike laboratory experiments, this one is not designed. It is natural, uncontrolled, and happening high above you. Yet it is still governed by precise physical rules. Cameras and sensors can extract measurements from these brief events. But even without instruments, the sky shows variation that reflects real parameters. This is why meteor watching stays compelling. Each luminous trail is another run of the same experiment, begun with slightly different initial conditions, and the outcome is visible at once. The atmosphere acts as the apparatus, and the meteoroid serves as the test sample. When you observe a meteor, you're watching debris from the solar system returning home. Meteors are not arrivals from beyond our neighborhood. Most are pieces that have been circling the sun for immense lengths of time, belonging to the same reservoir of material that formed the planets and still moves among them. Some originate in cometary trails. Others come from impacts within the asteroid belt that generated clouds of fragments. Over long periods, gravity and orbital resonances guide small pieces onto paths that cross Earth's orbit. When one arrives, it is not entering a foreign world. It is rejoining the environment of a planet that shares its origin. The atmosphere makes that reunion visible by converting motion into light, then taking the material apart into vapor and dust. Even when nothing reaches the ground, the material has still been added to Earth's system, mixed into air, and eventually into surfaces. This is why shooting stars feel meaningful. They are reminders that the solar system is not finished and not sealed. Material still moves, still collides, and still returns. A meteor is a moment when that ongoing circulation becomes visible. As we come to the end of this quiet exploration, you might notice how wide the night feels. Now, we followed tiny fragments of the solar system as they brushed our atmosphere, tracing brief lines of light that carried stories far older than Earth itself. From slow drifting sparks to sudden brilliant flashes, each shooting star reminded us that space is not distant or separate, but constantly passing through our sky, leaving only moments to notice before fading. Renewer again. We've wandered through ancient records, silent deserts, dark oceans, and the thin edge of the atmosphere where air first begins to glow. We've seen how the planet protects itself, how dust settles unnoticed, and how even the smallest streak can reveal motion, material, and time all at once. These events are fleeting, yet they repeat endlessly, night after night. Whether we are watching or not, now there's nothing left to follow, no paths to trace, no questions to hold. Just the steady presence of the night around you. If you've enjoyed these gentle journeys, you're always welcome to like, subscribe, or leave a quiet thought below. And if you happen to still be awake, another video will be waiting on your screen, ready to carry you a little further into rest. But for now, that you're breathing slow, allow your thoughts to loosen and drift the way dust settles after a meteor has passed. The sky has done its work. You don't need to do anything at all. Sleep well and good night.